So thanks a lot for inviting me here to give a talk. I'm not here since like 9 years, 7 years, just like 2 months. So I will be sharing a little bit of the work that we have done at ETH Zurich on quadrupedal robots, but also what we're doing here between UC Berkeley and Stanford. So the talk is titled Embodied Foundation Models. But before we get started, I would like to kind of categorize robotic capabilities according to these two axes. On the one axis, you see the mobility, and on the other axis, you see the autonomy. And basically, all in industry that we have seen so far that's used heavily are these industrial robot arms. They have very low mobility, very little autonomy. They perform the same task over and over again. More interesting already for us are these systems like self-driving cars or warehouse robots that have like an increased autonomy, but are still limited to a small set of environments, for example here, warehouses or on-road scenarios. So obviously what we want to do is have like robots that have like a really high level of autonomy and also a very high level of mobility. Examples include, for example, here like last mile delivery, so bringing packages to people at home, going up these stairs, but also space robotics, where we have to go into caves and do like really, deal in really harsh environments. Also performing search and rescue, for example, in firefighting scenarios, or lastly, monitoring like natural habitats, so really having those robots autonomously like surveying forest environments. So when we look, we can see that with an increase in mobility, we can access more and more environments. And with an increase in autonomy, we can perform more and more tasks. But what does it really mean to be like autonomous for a robot? So autonomy can be generally simply defined as the ability to independently perceive, understand, and act. So in the simplest case for a robotic system, what we want to have it to do is like sense the environment information, then perform some sort of computation on this perceived information, and based on this, select the correct motor actions to interact with the environment and perform a certain task. If we speak about autonomy for the task of navigation, what we are referring to very often is like achieving a certain goal. For example, finding here a safe path that leads the robot from its starting position towards its goal position. When we look today at the capabilities of legged robots, we can go a little bit back, like around 10 years, when basically my professor started his lab. They built the first quadrupedal robots, and they basically were walking very gently, slowly, based on model predictive control strategies, and you can see the static gates. Nowadays, we have way more advanced systems that are controlled by reinforcement learning policies that can go and jump up those boxes. So when we think about like navigating in those environments, we actually have to reason about the terrain. So for example, like what's the height of the box, what's the environment, but also the hardware. So the robot on the right, you can see, is way more powerful than the robot on the left. And finally, one of the most important parts is actually like the controller and the software that we're running on those systems. So basically understanding navigation in this context is absolutely non-trivial and a highly complex function. But to just bring us a little bit back, before talking more about navigation, I will just give you a really quick primer on like RL locomotion. So I'm not sure if every one of you is familiar. So like this diagram might look a little bit complex, but generally what we try to find is we try to train a policy that we labeled here as pi to provide us with a set of motor commands. So basically, where should our motors be for the robotic systems? Then these motor commands, like these target positions, are fed into like low-level PD controllers that apply then a torque. And we use a simulator as an input. It receives this torque signal to basically step forward the simulation environment. And then we can perform like reinforcement learning on this. So these simulation environments, based on the task definition, give us usually back some sort of reward function that we can use in an RL loop to optimize this policy. When we then want to go from the simulation to the real robotic systems, we just take our simulator away and plug instead in our real robot, and we perform a sim-to-real transfer. And basically, if you're interested in these topics, like these 4 works that are linked here are basically the cornerstones of all of the like leg locomotion RL control that has been done so far. And I really highly recommend to like read this. And this obviously is a little bit oversimplified, but you get the general idea of we train something in simulation and we can deploy it on the real robotic systems. How this then looks, for example, in a recent project that we're doing here in Stanford, you can see the Boston Dynamics robot here controlled with RL, following this target velocity command that we provide here. So the reference command is the green arrow, and the blue command is like what our policy in this case like achieves to track. Then typically also for training those policies, we not train on a single environment, but we simulate on like thousands of robots in parallel to all perform and learn the walking here. So with this, we have kind of finished a little bit this primer on our locomotion, and you will see later in the talk why we will need this and why this shows a little really greatly on like the kind of limitations of the current paradigm that we're using. But the talk is titled Building Towards Embodied Foundation Models. So what I'm going to talk actually in terms of research today will be like three aspects of this. On the first hand, we look at like diversity. So how can we bring more diversity into this learning paradigm? The second aspect will be how can we leverage abstractions to actually learn here? And the last aspect will be on the generalization of these policies that we are learning. So starting out with diversity, we start out with a pretty strong claim here that maybe some people would disagree, but I would say AI systems do not work outside of the training domain. To make the VCs more happy, I would say in most cases, but like a simple way to break most of the policies or everything that we learn with current neural networks is simply like change the training domain, go far enough away, and you will see that your policies are failing. So one interesting aspect that we want to do in a data-driven way is actually understand when those systems fail, when do our quadrupedal robots fail. And for this, we start out with collecting actually a very big data set of deploying these robots in various environments to understand, get a better understanding. Can we actually use them for like disaster response, going into mountains, going into caves? So this was like an endeavor that we did over like multiple months in Switzerland. So we brought the robots from like caves to like 3,000 meter high mountains and basically collected a very big data set that's openly available. Just to give you some understanding of how such a deployment looks like, we can see here in red, this is our quadrupedal robot, and it is attached a sensor payload where we have multiple sensors, so like multiple LiDARs and geometric sensors and cameras that allow us to sense the environment. We can then take this information and aggregate it and fuse it over time, so over time and also spatially to, for example, form such an elevation map, and also see if our state estimation and other classical algorithms that we require for mobile robots actually work across like a diverse set of environments. We can then take this information, for example, and aggregate this also in like a volumetric mapping framework here to build up maps that the robot is receives some geometric understanding of how the scene looks around it to navigate better. We can also, for example, then further go and take like the images that we recorded during such a deployment and create some Gaussian splattings of it, that we can create like 3D environments that look very realistic. And we will be revisiting this part later in this talk. So if you're interested in working with this data, when you want to have access to like a large amount of like robotic quadrupedal data, you can check this out on our webpage. We released this a few months ago, and we have already like 90 different research institutions all around the world working with this data. But now we have just seen like some data, but we have not seen really that there's any benefit or how this can improve the performance of these robots that we're using. So one of the first questions that I would like to look into is like, how can this data, for example, benefit the current paradigm of how we train locomotion policies? So for this, we need to take a step back into these simulation environments where we actually perform the training and the learning of these policies. So what you can see here is a very typical setup. We can see those boxes, those discrete stairs, and they're all created based on heuristics and some rules that some person came up with that will work well in these environments. So we can see this is a very oversimplified version and does not really reflect the complexity that we will experience in the real world. Therefore, those systems also don't transfer to everything that we will see in the real world. Furthermore, we can see those red dots that are spread around the robot. These red dots are basically a geometric perception that these policies usually receive as an input. So these simulators are basically bound to simulating geometry and also only providing geometric observations in first place. And rendering camera images or visual information is way harder. So in this work, which we call GaussGym, that is like just released recently, we basically addressed both of those points. So this project was led by Alessandro at UC Berkeley, who's really amazing. That was like the first author on this work. And the idea is basically that we equip a robot in simulation with a camera that sees with a front-facing camera the stairs here, and then the robot learns to decide correctly placing the feet of walking up those stairs directly from RGB vision. So what we need to have to make such a training work is on the one hand like a really fast visual rendering engine that allows us to perform a reinforcement learning in a quick manner that we don't need to wait for ages to get the results back. Also, we want to have really accurate physics available to basically train this locomotion policy. And lastly, we want to have a really diverse set of assets because, as you can imagine, like stairs can look way more different from an RGB perspective than they can look different from a geometric perspective. So we actually need to really think how we can get those assets, because I can't write down all the colors that stairs can appear in anymore. So if you get it all right, as Alessandro in this example did, you can create a policy that can walk up purely from RGB to walk up those stairs and walk down those stairs and really use RGB vision. And I think it's like one of the first policy where we could demonstrate some sort of useful sim-to-real transfer from locomotion to basically learn to walk upstairs directly from pixels. Then the question is like, how do we build this? And the first thing is basically focusing on like, where do we get the data from this? And what we could not do is write those handcrafted heuristics down. So instead, we retrieved to the way that we can just have a lot of different data sources where you can create these like simulation environments. One option is, for example, to just scan a room or a scene with your smartphone. Or you can use these existing data sets as like this Grand Tour data set that we have seen before. Or even cooler is, we can use basically video generation models to generate 3D videos and lift them into 3D. And how this lifting and discomposing of scenes is done as following. We use VGGT, which provides us, based on a set of camera images, like the image intrinsics, these image extrinsics, but also a point cloud and the spatial understanding of the scene, which is like a neural network that basically helps us doing this task. And then we can train like Gaussian splats based on the visual information given the post images. And we can use like a neural surface reconstruction to obtain like accurate geometry of the scene and combine this with an existing physics simulation to create basically Gauss gym. One of the cool things with this video generation models is actually that we can ask the video generation model to collect like any arbitrary scene. And if you think about in a robotics context, some data is really hard to collect. For example, like in disaster response, or if there's an aftermath of an earthquake, like we cannot easily simulate this. But with this video generation models, we can actually get some really cool data. You can also go and generate like data that might be like less useful, as for example in this avatar scenes or for this Blade Runner scenes, but which are very visual appealing and quite cool to see, that we can actually bring those robots on other planets, make them walk on the moon or on the Mars, or at least on something that looks like the Mars or the moon, and these video models can generate. Then putting it all together, we basically provide like a very big asset of like these 3D Gaussian splats, like thousands of them that you can use in your research to create like visual locomotion policies and train it then all in simulation, where you can see here like a preview of like a lot of images that these robots see while they try to learn up to walk those stairs. So if you're interested in this project, there's also the link for this, and we hope that we enable a lot of research in this visual locomotion policy learning based on this. So we have seen with regards to this diversity that we took now like the first step of making those simulation environments more diverse. But I would argue there's also another approach in terms of like, instead of making it more diverse, we can think about making the policies that we basically train more adaptive. So this general idea in learning is that we would ideally have like a function trained, or anything that we are training, be compatible with all possible environments and all possible inputs. But training something on this really big domain can be very complicated. What is more practical is actually like training a policy that is really effective on your current environment, in your current domain. But to train such a policy, we actually require some sort of signal if we're performing well or bad in a task. And we did basically a study around this adaptation topic, where we looked at estimating how easy or hard it is for a robot to traverse a certain environment. And in this setting, we can leverage a very simple like metric of how hard or easy it is to walk in an environment. Is we take the reference velocity that we can command to a robot by giving a velocity command, and then basically measure the difference with the velocity that it can actually walk to. So by taking this difference, we can derive a proxy that reassembles like some metric of easy or hard to traverse. So here you can see the robot walking from the left to the right. The blue is the achieved velocity, and then based on this, we can derive this like traversability score for this terrain. Using then such a score, what we can do is actually train a classifier to predict from images directly in the real world during deployment a traversability score. So what you can see here on the top right is actually like the input image that we feed to a neural network, that we train during the mission while the robot interacts. And basically this bluish color that you see on the bottom right means I am uncertain. This is a randomly initialized neural network. So now on the bottom left, you can see an operator commanding the robot to walk in an environment. And during this time, this network is actively learning and updating on the system, like in real time, to get more and more better predictions of where it can walk and where it cannot walk. So this requires only a few minutes of adaptation in this first version of this work, that then the operator can go, put down the controller, and then we can basically navigate in this environment around fully from vision. So we then deliberately placed some goals behind some trees based on waypoints, and then we can switch to a mode that the robot basically functions fully autonomous and just makes use of the traversability that comes from vision to navigate around here in this environment. Given that this worked actually quite great, we expanded even further on this work and made it adapt significantly faster, that we only take a few steps to get really fine-grained segmentation of where we can walk in an environment. And we can see those cool effects. For example, here there's an orange floor. I'm not sure how well this is visible, but before the robot ever interacted with this orange floor on the ground, it thought, okay, this is dangerous. I've never been there. I should not go. When we force it to walk over, it immediately adapts and provides after a few steps the correct signal. Also, one benefit that gets here very clear in this environment is that vision is really something that we should be using to walk around or navigate with robots, which is not done currently a lot in industry. So you can see here the glass, for example, this would look completely traversable from a geometric perspective, given that our LiDARs and other sensors cannot pick up based on those signals. So there's a lot of cool things coming together that help us to actually tackle this diversity problem. So this adaptation and increasing the diversity of the simulation environments that we're using along all the axes. Then at a second foundation that I would like to show you a little bit is about thinking about abstraction. And one of these models that have a really good abstraction and that is language are currently our language models, right? There's a lot of things that we can encode very easily in language of where to move, how to go, how to understand the environment, how to decompose things. And there we have a lot of knowledge where we have actually a really big domain available that we can perform the training on, which we don't have in a lot of other robotics applications. And what we wanted to understand in this project, and basically Tim led this project here, was basically assessing the performance of vision language models in terms of predicting where we should navigate. And what we did for this is basically we said we wanted to give our language model a certain task, for example, go downstairs, and then predict us a trace. And a trace is defined as a sequence of points in the image space to achieve this task. And then we told the language model, you're a legged robot or you're a human, what is the correct way to navigate here downstairs? And then the model was tasked to draw these correct paths leading it downstairs or taking the elevator in this case. And there's two assumptions that we make in this work, and I think they hold in practice. I would argue that most navigation tasks that we have in robotics today, if you can draw a trace or an image, a path on the image correctly, we have good enough systems to follow those traces or those paths in the image space. And with this, we could solve already 99% of interesting navigation tasks that we would be interested in practice from just an image and drawing on the image where to go. This would already solve a lot of tasks. So the main contributions here in this work were actually formulating basically navigation as a visual question answering task. And then we collected 1,000 samples of interesting navigation scenarios and hand labeled over 3,000 different traces. Actually, we had a small army of students that supported us labeling those images, which was very helpful. And then we provided basically a metric that could tell us the trace that's predicted by the model, how well does this align with human preferences of how good or bad this trace is. And then we did a comprehensive study where we actually tried to benchmark humans, but also benchmark the current state-of-the-art models, where we can see when we look at the results that the humans actually perform by far still the best, and we can find a big gap between the humans basically providing those traces and these language models. We also found that one of these dominant failure cases for those language models to fail is actually identifying what to do and where to go. So understanding where's the goal for a given navigation task. And we saw that basically those models most interestingly suck basically uniformly. So like if a model is bad, it's bad across all the axes. So it's bad across different embodiments, but also it's bad across different navigation challenges. So we could not pinpoint out like, oh yeah, it only works if you're a human, or it only works if you're in non-dynamic environment. It was really like uniformly bad compared to humans. So there's a lot of work that we need to do, I think, to increase this understanding of those models for these navigation tasks. And that brings us to like this third pillar of like, what can we now do to leverage this like foundational understanding that we actually see in the reasoning and in the language understanding of those models, and combine it with our super highly capable RL navigation policies. So for this, I will pitch you just like the brief outline of the Tiamat project. So this is actually like a very big project where in total, I think like over 20 universities are working on this project all across the United States. And this Tiamat project stands for Transfer from Imprecise and Abstract Models to Autonomous Technologies. And the ideas, the underlying ideas, no matter what we do in simulation, we will never get the perfect simulation right. I think that's everybody can agree on. So we always need to form a certain set of abstractions or other things that we can then transfer from the simulation to the real world. And in these benchmarks, or in this kind of Tiamat challenge, we are provided with basically a very complicated task instruction that can be any navigation goal or any basically open world instruction that a robot should follow. And here, for example, I provide this like, quickly follow the roads to the site, locate a cluster of buildings, systematically search for them, and then you might need to find like some objects that are useful for a certain mission or so. And what basically part of this challenge is that we are provided with a lot of digital twins of different environments where we have to perform those open world navigation tasks. And people won't tell you what kind of tasks you're looking for, but you can just imagine like you need to be able basically to follow any task instruction that comes with natural language. So you need to generalize a lot of different natural language commands. And what we're doing to try to achieve those tasks is actually build like a Tiamat architecture where we try to actually go from like a language model to like an embodied language model that shapes the behavior of the robot. So as a rough outline that I can provide you in terms of detail, given that there's a competition with a lot of other teams happening at the same time, it's basically we try to fine-tune like such a language model with inputs from a task description, with the environment description that represents the environment around the robot, and with some embodiment tokens, which is basically latent states of these RL locomotion policies that are learned with millions of environment steps in simulation, but represent the knowledge that the locomotion policies have around the environment to this like high-level reasoning model. And then also we have additional signals that we get from the simulator, for example, like how much time do you have left to fulfill a certain task. We put it all as an input to like a large language model and then try to predict like which behavior should we be using. And this behavior can then go and select, for example, like I want to use like my navigation agent or my exploration policy, and then provide a certain set of goal commands to fulfill. And this system, we are basically adapting and fine-tuning all in closed loop. So now to wrap up a little bit of like this talk of what we have seen so far. So we have seen that we basically looked at this problem of diversity, where we have seen like 3 different works of increasing the diversity that we can be using across like this data domain, across like improving the simulators themselves by including the visual domain, and also the increasing in assets. Then we have seen that we can perform like some adaptation of these policies, that we can get some signals while interacting with the environment that can be useful for learning. And we have seen that like leveraging these abstractions or understanding where these models can actually be useful for us to work with, it's very useful. And lastly, we have seen that we started now here working on this kind of topic of generalization and performing really open world general purpose tasks that cover this navigation problems. So if you're interested in any of this, I'm happy to take questions, and also feel free to reach out to me. Yeah.
Stretch, but if you wanted to apply these same ideas to manipulation with robot fingers and such, what do you think the challenges are? And one way in which you can think about this is, for example, there's an NSF workshop that Mark Kokoski participated in where they're thinking of manipulating objects as kind of the inverse of locomotion, right? Locomotion, the robot manipulates itself through fingers that touch the world, but the manipulations with hands touching objects. What do you think are the challenges of moving this into that domain?
Okay, so I will try to comment on this in this like sim to real paradigm, which we see that works just really well in locomotion. So the difference is for locomotion at first, we don't care about the forces that we apply to the environment in nearly all the cases. So it doesn't matter how hard I'm stamping. This is completely different from manipulation. So there you really care about the forces that you apply in your environment. Therefore, these kind of the forces that are predicted by the simulation environment, they are not super accurate, but we would like to have them really accurate for manipulation. That's the first difference. Then the second difference is you can also see that all the videos that I've shown from like real robots walking around, they had like 4 legs. And this is just because like 4-legged robots are way more capable even today than 2-legged robots because the solution space is way bigger. So kind of like we can always react, we can always take a foot, take a side step, and basically we have a lot of more solutions to like this task of like walking forward, and we have a lot of redundancy in just how we build those robots, which I would say in manipulation, the solution space is actually like extremely small and slim. If you try to pick up this egg, you need to have the exact correct forces available. So kind of taking these two things aside, I think it's currently like open if simulation is the way to go to kind of transfer policies from sim to real for manipulation. And we have seen like this kind of pretty good results on imitation learning. So I would say that's like a good start, but I hope that in the end we will do some sort of like RL fine-tuning in the real world also for this. Yeah.
I would actually like to build on Allison's question. If you go back to the very early slide you showed, sort of tutorial on reinforcement learning.
Yeah.
You have a diagram.
Oh, yeah, sure. Find it.
It may be that what you just said to Allison is an answer to my question about this. When I looked at that, my first thought was, well, wait a minute, why are we going to actuator position targets and then going through a controller to get torques? Why not use like a sonic ATIV, some operational space control, and go directly to forces? And so maybe your answer is, well, actually, because that's not what you care about so much for quadrupedal locomotion in the world. And maybe I'm thinking differently because my own experience is more with climbing robots, which are actually closer to hands.
So I can give the answer really precisely why we need to use this like position control for the robots. So when we do the RL training, we start out with position control. And if the policy learns nothing, it basically knows to predict the default positions. This will make the robot stand stable per default if it has 4 legs. So you start out with a good initialization of your task of just standing. And then in the RL training, you can imagine we apply like some sort of random noise or like time correlated noise to discover those skills. If we start with force control, we already need to compensate for gravity, know how we are standing, and the search problem gets extremely hard. So we tried this actually a lot to make force control work, and we always saw significantly worse performance. Like we tried it in multiple projects, and there's one initial study, I think from MIT, done by Pulkit, that made it work, but still the performance looks significantly worse than with these kind of setups. Yeah. Okay, then I guess thanks a lot.